All right, in this section, we're going to look at further applications of right triangles. And in order to get starting, we're going to need to talk about angles that are used in a navigational context, and this is known as bearing. Let's look at a quick example.
High-speed cruise, torpedo in the water, bearing 315.
Make range 7,000 yards.
Steer right, 315.
Wait a minute, that's heading into torpedo.
Steady bearing still 315.
Estimate range 6,000 yards.
Still 315.
Steer right till this reach, 315.
No, that's wrong. Ryan, don't turn that goddamn wheel.
315.
You're heading straight into that torpedo.
Yes.
So what did Captain Ramius mean when he said to turn the Red October to a bearing of 315? Well, what he meant was 315 degrees from north. So bearing is a single angle given, and it's understood that it's measured clockwise from due north. Since everyone on Earth can agree where north is, bearing is a really great way of providing direction in navigational situations. Okay, well, let's have a quick look at the four cardinal directions. So north is that way and south is this way, and then we have west and east. So a bearing of 315 degrees would be read from the north, 315 degrees. Well, there's 90 degrees. And this is clockwise. And there's 180 degrees. And there's 270 degrees. Okay, so it's another 45 degrees from there. So this is the direction that Captain Ramius was directing the submarine to turn into. So you have to understand this is a completely different context than angles in standard position. Angles in standard position, at least positive ones, are measured counterclockwise, and the initial side is always the positive x-axis, which would sort of correspond to east here. Now, in bearing, it's just a completely different context. Positive angles are read clockwise from north. But not always, because bearing can also be presented as an acute angle relative to one of the cardinal directions. For example, you might have south 42 degrees east. What this means is start pointing south, and we know east is this way. So measure an angle 42 degrees from the south in the direction of east. So that would, in this case, be a bearing that's read counterclockwise. All right, well, let's see bearing used in an example. Okay, so here we have two radar stations, and they're positioned on the same latitude line, the same east-west line, 8.6 kilometers apart. Okay, so let's call this guy Station A, and we'll call this guy Station B. And we're just going to decree that those are 8.6 kilometers apart. Very good. Now, somewhere in the distance, there's a plane, plane C, and Station A, using radar, can detect the plane and notes that it is at a bearing of 53 degrees. So let's draw a bearing of 53 degrees at Station A. All right, well, we need to figure out where that is, so let's start with north. We agree that north would be that way. And a bearing of 53 degrees would mean 53 degrees read clockwise from north. Okay, well, 45 degrees is about like that. 53 would be a little bit more. So there's our bearing of 53 degrees from north. So all Station A knows is that that plane is somewhere along that line. It could be very close, it could be very far. So we need another station somewhere else to detect the plane at the same time, and then we'll triangulate its specific location. So of course Station B detects the plane at a bearing of 323 degrees. So let's draw a bearing 323 degrees at Station B. Again, they agree on north. Okay. So 323 degrees would be read clockwise from north. So there's 90, 180, 270, and then there's another 53 degrees. So maybe something like this. So there's our bearing of 323 degrees. Okay, well that means that the plane must be right here. Okay, the question is, how far is plane C from Station B? Well that's simply asking for this length right here, which if we conform to the convention for triangle labeling, we should call this little a since it's opposite vertex capital A. Okay, well obviously we're going to need some trigonometry, and we need to figure out at least some of the angles in this triangle. And we don't know any at the moment, but they're not too hard to figure out, so let's go and do that. First of all, we can figure out what this angle is right here, because that's the complement of 53 degrees. So that'll be 90 degrees minus 53 degrees, which would be 37 degrees. Okay, and we can also figure out this angle because it's a bearing of 323 degrees that got us there, but you can see that 270 degrees constitutes this amount, so the difference would be 323 degrees minus 270 degrees. Okay, well that's 53 degrees. And finally, we need to know this last angle here. We can see that, of course, the three angles in a triangle must add up to 180 degrees, and 37 degrees are here, and 53 degrees are here, and together those add up to 90 degrees, which means that that third angle must in fact be itself a 90-degree angle. Which is a good thing, because if it weren't, then we wouldn't be able to use the right triangle trigonometry to solve this. So it's very convenient that this plane happens to be located where it is. If this turned out to not be a right triangle, like if the plane were just somewhere else and it weren't a right triangle, then it would take a lot more machinery to solve this. And we're going to be solving problems like that in Chapter 7, the end of this semester. Okay, so we have a right triangle, and we have a side length, and we're interested in A. So all we have to do is appeal to one of the trigonometric functions and one of these acute angles. Let's just use the 37-degree angle here. So relative to this 37-degree angle, we can see, well, the 8.6 is the hypotenuse, since it's opposite the right angle. And this little a over here is opposite of angle A. So what trig function involves the opposite side in the hypotenuse? Sine. Okay. So we know that sine of 37 degrees is little a, the opposite side, divided by the hypotenuse. So solving for a, we're going to get that a is 8.6 kilometers times sine of 37 degrees. On a calculator, I get that a is 5.175609199 kilometers. But that's way too precise based on the measurements given in the problem. We're only measuring things up to the nearest tenth of a kilometer, so we can only assume an answer up to the nearest tenth of a kilometer. So let's make our final answer 5.2. Okay, very good. Okay, so here we have a geometric situation, and we're interested in knowing the value of h. Now this is in a sense, very similar to that problem we saw in the last lecture, where we were interested in knowing the height of a tree. And so we measured along the ground at the base of the tree, and then used the tangent function to find the height of the tree, and it was pretty straightforward. However, what if you want to know the height of an object that is not accessible to you? For instance, you can't just walk right up to it and start measuring. So in this case, we would take some measurement a certain unknown distance away. Let's call this distance x. So we would see that when we are an unknown x distance away from the building, the top of the building has an angle of elevation of 74 degrees. Then we can move back a fixed length that we can easily measure, like 35 meters, and then take another angle measurement and see that the angle of elevation to the top of the building is now 52 degrees. And with that information, we could now determine the height of h. So what do we have here? Well, we have two triangles. We have sort of an inner triangle and an outer triangle. And what we're going to do is we're going to relate x and h in two different ways and come up with a little system of equations, and we're going to solve for both x and h. And in the process, we'll of course be learning what h is. So let's look at the inner triangle. What does the inner triangle tell us? The inner triangle tells us that tangent of 74 degrees is h over x. And what does the outer triangle tell us? The outer triangle tells us that tangent of 52 degrees is h over x plus 35. So now we have two equations and two unknowns. So what we need to do is isolate one of the variables in one of the equations and then substitute for that variable in the other equation. Okay, well, let's isolate x in the first equation. Okay, well, tangent of 74 degrees is equal to h over x. Well, therefore, x is equal to h divided by tangent of 74 degrees. So now we can take that x value and plug it into the other equation, and we'll have only an equation involving h. Okay, well then we can just solve for h. So the other equation is tangent of 52 degrees is equal to h divided by x. Now x is being replaced by h over tangent of 74 degrees. And then we're adding 35, and this is all in the denominator. So now all we have to do is solve for h. Okay, well, the first thing we ought to do is clean up this fraction within a fraction on the right-hand side. And the way we're going to do that is by multiplying the top and the bottom by tangent of 74 degrees. So the numerator becomes h times tangent of 74 degrees, and the denominator becomes, well, this tangent of 74 degrees distributes, giving us just h plus 35 times tangent of 74 degrees. And on the left we have tangent of 52 degrees patiently waiting. So that's a little bit cleaner, easier to work with. Now let's multiply both sides by this denominator, h plus 35 tangent of 74 degrees. So we get, on the left, h plus 35 tangent of 74 degrees. That's all multiplied by tangent of 52 degrees. And on the right, we're just left with the numerator. Okay, remember, we're trying to isolate h. So at this point, let's distribute the tangent of 52 degrees. So we have h times tangent of 52 degrees plus 35 times tangent of 74 degrees, tangent of 52 degrees equals the right-hand side here. So we distributed tangent to 52 degrees. Now let's bring the h's to the same side of the equation. So we'll move the h tan 52 degrees to the right. So we have 35 tangent 74 degrees, tangent 52 degrees is equal to h times tangent of 74 degrees minus h times tangent of 52 degrees. And now we can factor h out of the right-hand side. Dividing by all of this, we'll finally have h isolated. So we can say that h is equal to 35 tangent of 74 degrees, tangent of 52 degrees, all divided by tangent of 74 degrees minus tangent of 52 degrees. We really had to dig for our algebra skills to solve this particular equation, but we got it. We got what the h is. Let's use a calculator now. So when you're using your calculator for this, be very careful. You might want to do this in small pieces. Perhaps you'll want to work out the numerator and then independently work out the denominator and then go one divided by the other if you don't want to make a mistake. But if you're confident in your use of parentheses with the calculator, you can do this probably in one go. Okay, I got that h calculated to 70.77280,495 meters. The original problem statement involved a 35-meter length, so that's two significant figures. So to the nearest meter, this rounds to 71 meters. And we're done. I would just like to add that we got an answer of little h equaling 71 meters, and that doesn't really agree with this drawing, especially if this length is 35 meters. H should be about twice as tall as it is. Well, that's just because this is not a faithfully drawn diagram. So 52 degrees would be a much bigger angle than that, and 74 degrees, same thing. If I include a diagram on a quiz or an exam, it's not necessarily going to be a faithful representation of the different measures in the problem. So just trust the mathematics, not the diagram. All right, so here we have a person in a lighthouse who's tracking an approaching whale. So this person observes the whale starting here, where the whale is in the drawing, and moving slowly or quickly, however, to this location. And the question is, how far did the whale move? So what is the length of x in this process? Now, the researcher knows the height of the lighthouse, which is 68.7 meters. The researcher also was able to take two angle measurements that are angle of depressions, so read downward from the horizontal. One measurement at the beginning of tracking the whale, which was 15 degrees 50 minutes, and finally a second measurement when she stopped tracking the whale, which was 35 degrees and 40 minutes. Okay, so what's the length of x? Well, we obviously have the two triangles similar to what we had in the last problem, with an inner and an outer triangle, and they're both right triangles. And we can certainly determine angles within those triangles because we can use these angles of depression, which are complement to the angles in the triangle. For instance, this angle right here is the complement of 35 degrees 40 minutes. So if we quickly did that math, we would have 89 degrees 60 minutes minus 35 degrees 40 minutes, and we would get 54 degrees 20 minutes. Okay, and this angle right here is the complement of 15 degrees 50 minutes, so that would be 90 degrees minus 15 degrees, 50 minutes. So we could write that as 8960 minus 1550. And we get 74 degrees, 10 minutes. Let's also label this length right here as y, and let's agree. So now, there is a lot of clutter here, but we can look right through it. And let's take a look at this first triangle. Can you see that tangent of 54 degrees, 20 minutes is y, the opposite side, divided by the adjacent side, which would be the height of the tower, 68.7 meters. So we have that tangent of 54 degrees, 20 minutes is y divided by 68.7 meters. Well, that tells us that y is equal to 68.7 meters times tangent of 54 degrees, 20 minutes. Okay, well, let's look at the outer triangle now. The angle we're interested in there is the 74 degrees, 10 minutes. And we can see that tangent of that angle is the opposite side of that outer triangle, which would be x plus y, all divided by the height of the tower, which is the adjacent side of that angle, and that's 68.7 meters. So x is what we're after, so let's solve for x. Well, we can see that x plus y is equal to 68.7 meters times tangent of 74 degrees, 10 minutes. So subtracting y, we would get 68.7 meters times tangent of 74 degrees, 10 minutes minus y. But we know what y is because we figured that out right at the start. Y is 68.7 meters times tangent of 54 degrees, 20 minutes. So we have x equals a bunch of stuff, and let's use our calculators for that. Remember, for taking the tangent of degrees plus minutes, you would write something like 74 plus 10 divided by 60 in your calculator. Okay, and the original problem was given with the precision down to the 10th of a meter. So why don't we do that here and say that the whale swam 146.5 meters while being observed. Very good.